assistant professor in the Department of Earth Sciences in the University of Western Ontario. She got her PhD in the University of Arizona, working on Titan surface properties, as well as on astrobiology, studying how amino acid could be formed under the Titan atmospheric conditions. Then she got different postdoctoral positions, like a fellowship at Johns Hopkins University and another one in NASA Goddard Institute. Her early career has been awarded with the Ron Greeley Award, given by the American Geophysical Union in 2014. So basically, she's an expert in the analysis of surface properties of all rocky planets and satellites in the solar system. So such as the Earth, the Moon, Mercury, as well as those with thicker atmosphere like Venus and Titan. She mainly uses radar observation for her work. And for that, she's a member of the Cassini radar team. So hopefully I didn't forget something.
Great. Thanks very much, Elodie. Yep, so I'm one of the TEPS co-Is. Let me just introduce myself, add on to a little bit about what Elodie just said. So I'm a planetary geologist, although in a Department of Earth Sciences, although at times in my past I've also been a physicist, an astronomer, and a chemist. That's what I love about planetary science, is you get to be a really interdisciplinary scientist, and it's also one of the great things about the TEPS program too. But these days, as Elodie said, I mostly use synthetic aperture radar to study the geology of different objects in our solar system. And I've published on a variety of different objects in our solar system, from Mercury, Venus, Earth, Moon, and Titan. And that's going to be the focus of today's talk. So I didn't want to make it too general. I thought I would focus in on my favorite place in the solar system, which is Saturn's moon, Titan. And hopefully by the end of this talk, I will have convinced you that it is the most interesting place in the solar system. So here it is, my favorite world. And it's not that beautiful image of Saturn you see in the background with its rings and the shadow of its rings projected onto the planet, but rather that orange dot you see right in front of Saturn. In case you don't know what I'm talking about, let me just point it out for you. That is Titan. So Titan is the largest satellite of Saturn. It's also the second largest satellite in the solar system. It just got beat out by Ganymede, which is Jupiter's largest moon. And if it didn't orbit Saturn, you'd probably call it a planet. It's bigger than Mercury. It is planet-sized, and it has a thick atmosphere. And that thick atmosphere has caused some problems in Titan exploration over the years. And for many years, we didn't know much about Titan. It just remained that orange blob that you see here, and some of the first up-close images we got of Titan from the Voyager missions in the early 1980s. We knew so little about Titan when Voyager was built that we didn't know which instruments to put on Voyager in order to see through Titan's thick, smoggy atmosphere to the surface. And so we learned an awful lot about Titan's atmospheric chemistry and dynamics from Voyager. We learned almost nothing about its surface geology. Fortunately, from the information gained from Voyager and subsequent observations, we were able to develop instruments that could see through Titan's hazy atmosphere to the surface. And so when the Cassini spacecraft was launched, it had on board several instruments that could probe through the atmosphere and see the surface. And so Titan went from being this orange, shapeless blob to a whole world. And here you can see one of the first Cassini images we have of Titan. So we were able, for the first time in 2004, to see the surface of Titan. So it was only about a decade ago that we started to get information about Titan's surface geology. And what we've learned in that past decade has been really remarkable. Titan has turned into a whole new world that really looks amazingly Earth-like, considering it is an icy satellite 10 AU from the sun. So what have we seen there? Well, we've seen streams. So you can see this, imagine looking out an airplane window. That's sort of the view we're getting here. This was taken by the Huygens probe that descended through Titan's atmosphere in 2005. And I don't think I have a pointer, but the dark features you see at the top of this image are streams, or at least they used to be streams. But these were not streams cut by liquid water. Titan's surface temperature is 200 degrees below the freezing point of water, so it must have been some other fluid that carved the surface. And from what we can tell, it was likely methane. So Titan has a thick atmosphere of nitrogen and methane, and the methane actually condenses much like water does in the Earth's atmosphere. It rains out onto the surface and can flow like a liquid. And we've seen evidence actually of these storms. So that these white features you're seeing here near Titan's equator are clouds. And we've seen evidence of clouds coming and going in Titan's atmosphere. And even evidence that they rained. The surface will darken temporarily after a cloud passes by and then brighten again, which is very suggestive of rain hitting the surface and darkening it. And the rain, in addition to forming those streams we just saw, can also form large lakes. And so here is an image, a radar image of Titan's North Pole. And if I hadn't told you this was Titan, many of you may have guessed this was a region on Earth. The features you're seeing here, these large lakes and seas, are surprisingly similar to lakes and seas we see on the Earth. But again, that dark liquid you're seeing there is not water. It is probably some combination of methane and ethane. So we basically have this huge reserve of hydrocarbons just sitting on the surface of Titan in the icy bedrock beneath. So an amazingly Earth-like world. How do we know this is liquid? Well, in addition to the very, very dark radar return we're seeing here, which is suggestive of a very, very flat surface, we have other observations of Titan at infrared wavelengths, and here is one. And what you're seeing there is a little specular reflection from one of the lakes near Titan's North Pole. That bright dot you're seeing near the North Pole of Titan is a specular reflection. And you guys are probably all familiar with these sorts of reflections. Again, when you look out, say, an airplane window near sunset or sunrise, you might happen to get a glint off a stream or lake. Because of the flat surface, it acts like a mirror for the sun. And so that's what we're seeing on Titan, is the specular reflection. So suggesting we have very, very smooth bodies of liquid there. Near the equator, we find a massive sand sea. Titan is probably covered in more sand than any other body in the solar system. So each of these lines that you're seeing here, striping across the surface, is a huge sand dune, perhaps hundreds of meters tall, that wrap around Titan's equatorial regions, blanketing them in this sand material. And when I say sand, I'm not talking about the white sand beaches you might find on your vacation in Florida. The composition is quite different. So even though the morphology is the same, it's likely formed out of organic molecules rather than quartz like we see on the Earth. So we have some sort of organic sand dune that's just the right size to be blown around and formed into dunes near Titan's equator. And then finally, we also see some evidence, although very limited evidence, that there might be volcanoes on Titan. And we're seeing probably the best example here. This is called Sotrafacula. And you see at the bottom there a bit of a mound and a caldera possibly next to it. And then if you go to the top of the image, you're seeing what's possibly a flow. But volcanoes on Titan aren't exactly the same as volcanoes on the Earth or other terrestrial planets, because when you melt the bedrock, you're not forming a basalt like we see on Earth, but rather you're melting an icy bedrock to form liquid water. So lava flows on Titan would be made of water, because that's what composes the bedrock. And so this introduces a possibility of new reactions between the liquid water from flows and the organic molecules on the surface. And as I showed in my PhD, that you can actually form amino acids and other biological molecules through these sorts of reactions. So finding evidence of liquid water or past liquid water on Titan could tell you an awful lot about prebiotic chemistry and the origin of life. And then lastly, we see impact craters on Titan. So these are features that are formed when, in this case, a comet likely struck the surface of Titan, dug out a big hole, and left that hole and its ejecta blanket behind. But surprisingly, unlike most objects in the solar system, we see very, very few craters on Titan. Only just a handful, really. And here's the distribution of those impact craters as about a couple of years ago. And what you notice here is just the really limited number of impact craters that are available on Titan. If I were to show you this image of the moon, it would take you years to count, if not decades or centuries, to count the number of craters there. But you can see on this image of Titan, you could probably count the number of craters in about 5 minutes. And I'll spare you the trouble. There's about 60 of them. So 60 impact craters on a world the size are bigger than Mercury. So very, very few craters. And in this way, Titan is incredibly Earth-like. Earth is another object in the solar system with very, very few impact craters. So here's a similar map for the Earth with its impact craters labeled. And part of the reason we see so few impact craters on the Earth is because it has an active hydrological system that causes extensive erosion and erases craters, so they're very, very difficult to find. In addition, we have plate tectonics, which can erase craters. We also have a huge body of water on the Earth. You can see there's maybe 1 or 2 impact craters that have been found in the bottom of the ocean, and there's several reasons for that, and I'll get back to that later in the talk. No impact craters in Antarctica because it's covered in a thick layer of ice. Few in the Amazon, where there's high weathering rates, and also just fewer in places where there are fewer geologists. So you'll notice there's not a lot of impact craters that have been discovered in Africa, simply because the scientific research there is not as well funded as, say, Australia or North America. So this distribution of impact craters on the Earth is a combination of many factors, but it indicates that the Earth is a very active world. More processes are around that can destroy impact craters very quickly. So, why is this important? Well, we use impact craters to date planetary surfaces. You assume that a surface starts out blank and that impact craters accumulate over time, and so more impact craters equals an older surface. And if we were just to do this simple calculation for Titan, count the number of craters, compare it to the impact flux that we expect for the outer solar system, you get an age for its surface that's somewhere on the order of several 100 million years old, depending on exactly which parameters you use. But as I said, this is a bit simplistic because there have been a lot of processes that have shaped the surface of Titan. And in fact, if you look at the surface of Titan, the age is not constant as you roam around. So it's actually quite a bit older near the equator, where we find most of Titan's impact craters, compared to the poles, where we see almost none. So the polar regions of Titan are at least a factor of 5 younger than the equatorial region. So there's a lot of complications to trying to use impact craters to date the surface of Titan. But what's great about them is they also conversely tell us a lot about its geologic history. And what's particularly interesting about these dates is that they coincide with some of the ages of methane that have been predicted for Titan's atmosphere. So as I mentioned earlier, Titan has an atmosphere composed of mostly nitrogen with a little bit of methane. And this is actually remarkably unusual because methane breaks down very quickly under UV photolysis from the sun. So we wouldn't expect to see methane in Titan's atmosphere over geologic timescales. So the fact that it's there suggests that the methane in its atmosphere is relatively recent. What happens over time is that methane reacts with those ultraviolet photons to produce a whole range of higher order hydrocarbons, ethane, acetylene, propane, hydrogen cyanide, and so on and so forth. These rain down onto the surface to provide the sand dunes and all the other organic coating we see there. We lose the hydrogen to space and there's no going back. So we need a source of methane in order to keep it stable in Titan's atmosphere. And so there have been some estimates for the age of this methane, and like the impact crater population, it seems to suggest it's been around for the past few 100 million years. So the topic of this talk is how we can use impact craters to teach us about Titan's geologic history. So we'll focus on these three questions. Number one, why are there so few craters on Titan? Why do they have that odd concentration where most of them are at the equator and very few of them at the poles? And what is this telling us about Titan's story, about its evolution over time? So we'll start with a conversation about landscape modification on Titan. So what has been happening to Titan's surface to change it? And and how do we use craters to constrain these processes? So here's a bit of a mosaic or a compilation of several different impact craters on Titan, from the smallest at top left, Kasa, to the largest at bottom right, Minerva. You'll notice all of these craters are named after gods and goddesses of wisdom. So I've had some fun trying to find gods and goddesses of wisdom to name these craters after. And if you look just simply at their morphologies, you'll notice that many of them do not appear to be particularly fresh. They're not that nice bowl-shaped crater form you sort of expect. A lot of them seem to be weathered quite heavily through fluvial and aeolian processes. So it rains on Titan, that forms channels which cut into the crater rim. Sand gets blown into the middle of the crater, and it changes their morphology to what we see on Titan today. So how do we quantify this? How do we know how much weathering has been going on Titan? Well, one approach I've taken in one of my previous papers is to compare the craters we've seen on Titan, which you see here on the right, to pristine craters on airless satellites. And on the left, you see Ganymede, which has many, many similarities to Titan. It's about the same size. It's made of presumably the same sort of stuff, i.e. water ice, similar gravity. So many of the same properties that would affect the size and shape of impact craters on Ganymede also apply on Titan. So we can directly compare their craters to see how much erosion and weathering has happened to the craters on Titan. Just to give you an idea, this is what a fresh crater on Ganymede looks like on the left compared to a more degraded crater of the same size on Titan. You can see they don't look the same. Something has happened to modify the crater, most likely exogenic processes. And by comparing their depths, we can constrain the amount of erosion and the style of erosion that's occurred on Titan. So what do we start with? Well, we take topography of craters on Titan to figure out their depths. There's a couple of different ways to do this. One approach, which you see here, is to do stereotopography. This involves taking two images from slightly different angles and using the shadows in those images in order to infer the topography. And so that's what you're seeing here at the right for Kasa crater. And what we found was a depth of about 750 meters. Okay, so we can then compare it to a similarly sized crater on Ganymede to see if the depths are comparable or not. And so here is that chart. You can see the little boxes and stars are data that has been collected for Ganymede by Paul Schenk. And then all the gray dots are data I've collected for Titan using a variety of different methods. And what you notice is that they are all shallower than similarly sized craters on Ganymede. So something has been happening systematically on Titan to reduce the depth of the craters there. Some of them are reduced to practically nothing, which you can see down here at the bottom with depths of less than 100 meters. These are very, very shallow craters. They're very, very difficult to recognize, in fact. So we're going to quantify the difference between the depths of craters on Ganymede and the depths of Titan's craters using a metric known as the relative depth, or R. So we take the depth of a crater on Titan, we divide it by the depth of a crater on Ganymede, and subtract it from 1 to get a relative depth. And you can see that the freshest craters on Titan have relative depths close to 0, and the most degraded craters have relative depths close to 1. Okay, so this is going to give us a measure of how degraded a crater is on Titan. All right, and we can use this to infer the style of erosion happening there. So here's two hypotheses. Was it due to fluvial erosion or aeolian infilling? So fluvial erosion, it rains and channels form. Typically, what happens is that this erosion happens very quickly. The crater fills in, and then when the slopes shallow out, it's sort of, the rate of erosion also slows. So you'd expect most craters to have relatively high relative depths, upwards of 0.6 or more. And you can see an example here from Mars, where you get a flat crater floor. The rims of the craters are also pretty flat, and you see evidence of channels and so forth digging into the crater walls. Conversely, if you have sand being blown continuously into the crater to fill it up, you expect a more linear distribution. So craters will be anywhere from totally fresh to completely filled in. It just slowly happens over time. There's no preference for any particular relative depth. So we can compare these two hypotheses to the data that we've collected. So on the y-axis here, we have the relative depth of those craters. Again, the bottom 0 would be the freshest craters, and the top 1 would be the most degraded craters. And you can see the diameter range from the smallest craters on Titan to the largest craters. Okay, and it's a bit of a hodgepodge. The data is kind of all over the place. If it was fluvial erosion, we might expect most of the data to be up here at higher relative depths. Again, because the initial steps happen so quickly, it's rare that you would catch a crater just in those initial steps. Conversely, if they were all fresh craters, those relative depths should be closer to the bottom. And they're not. They don't fit either of these hypotheses. They're sort of distributed randomly. And that's, in fact, most consistent with aeolian infilling, just that slow process of dumping sand into a crater over time, which in retrospect makes sense because most of these craters are found near Titan's equator, which is a giant sand sea. From 30 degrees north to 30 degrees south, Titan is covered in sand dunes. So it's perhaps not surprising that the data ended up being consistent with infilling by sand. There is one final hypothesis, too, that I haven't mentioned, and that's something known as viscous relaxation. Because ice has such a low viscosity compared to rock, it can actually relax over time. It will flow, much like a glacier, over millions of years. And so a fresh crater that you see here labeled by a black arrow can turn into a very flat crater, which are labeled by the white arrows. The rim sticks around, but the crater floor bounces back and flattens out. So this is actually a question one of my graduate students is investigating. What is the role of viscous relaxation in crater modification on Titan? Looking at models for Ganymede, to first order, I don't think this is going to be a big issue for Titan because of the temperatures encountered there. Also, the rate of change of depth with time should mimic that of fluvial erosion, i.e. most of those craters should have very large relative depths, and that's not what we see. But to date, nobody's done this for Titan, so my graduate student is going to do that modeling and better constrain this process to see what difference it might play in reducing the depths of craters on Titan. So what's the punchline? When we've measured the depths of Titan's craters, we find that they are shallower compared to all of their Ganymede equivalents. This is not an accident. There is something happening to reduce the depths of craters on Titan. Given their distribution, we think the likely cause of this is aeolian infilling. So sand slowly filling in these craters in the equatorial regions. But what this doesn't explain is why we don't see many craters or no craters at all near the poles, which as far as we can tell are pretty much sand-free. So what's going on there? All right, so let's move on to section 2, where we investigate this question of the distribution of craters on Titan in more detail. So just to remind you, the craters on Titan cluster near the equator. the vast majority of Titan's craters are within 30 degrees north to 30 degrees south. There's only a smattering of craters near the poles, and most of them are questionable at best. This is not a function of uneven coverage. Cassini has obtained a lot of detailed coverage of Titan at both the equator and the poles. In fact, there's probably more data at the poles because of the lakes there that people are interested in studying. So there really is a deficit of craters in the polar regions. So why is that? So I racked my brains and I tried to come up with as many hypotheses as I could. I think we can rule out number one simply because we don't see any evidence of sand near the poles. So it's not that there is more aeolian infilling going on at the poles. If it is, the sand there is very different than what we're seeing at the equator. Another idea proposed by a colleague of mine was that there was a very late acquisition of the atmosphere that basically dumped a whole bunch of sediment onto the surface of Titan, erasing any craters there. But given how young the poles appear to be, this would have happened very, very recently, and there doesn't seem to be a lot of evidence for that young of an atmosphere on Titan. We could have had infilling by volcanism too, but similarly, there's not a lot of evidence for volcanism on Titan. Our best example, and perhaps only example, is the one I showed you at the beginning of the talk. So I'm left with two hypotheses that I'm going to investigate further. The first being that there is increased erosion near the poles that's preferentially erasing craters at a higher rate. And the second is this idea of marine impacts into liquids. Well, let's start with number 4. All right, so here are some models of the weather on Titan, essentially. So what you're seeing on the left is the average precipitation rate on Titan as predicted by models. And what you'll notice is that that average precipitation rate is higher near the poles during summer. So that NSS stands for Northern Solstice Summer, something like that. That's Northern Summer, which is taking place about now, 2017. We're in the heart of summer at the North Pole of Titan. And so there should be more precipitation there. And we've seen evidence of that, at least for the South Pole. Cassini arrived right around Southern Summer, and there was certainly increased precipitation near the South Pole then. However, when you're actually carving channels and eroding a surface, you might be more interested in the flooding rate or the instantaneous precipitation rate. Here the story is not as clear. There do seem to be large storms near the equator and the poles. But it's possible that we could have more erosion near Titan's poles. So to investigate this idea, I decided to take digital elevation models of craters on Ganymede, our fresh starting point, and then erode them using a landscape evolution model developed by my colleague Alan Howard. So we'd start with something like the crater Isis you see on the left on Ganymede, and then degrade it through fluvial processes to see if we could recreate similarly sized craters on Titan, like Sidlap or Soy. All right, so can fluvial erosion alone account for both the depth and the morphology of the craters that we see on Titan? So here's our starting point. Again, Isis crater on the left, which is a typical crater of its size, and then the digital elevation model on the right, developed by my colleague Paul Schenk using data from the Galileo mission. So you can see there's a higher rim, flat floor, and a little bit of a central pit. That's the depression near the middle of the crater that you're seeing there. These are very common for large craters on icy satellites, although we very rarely see them in terrestrial planets. So this is our starting point. Can you guys see the movies? Yeah, it looks like you're seeing the movies there. So then I put it into Alan's landscape evolution model and let it rain over time to see how that would change the morphology. So we could vary a couple of different parameters, grain size, the erodibility of the bedrock, the weathering rate. And you can see that given enough time and a high enough weathering rate, you can basically wipe a crater off the surface of Titan. So at the end of these simulations, you'd be hard-pressed to identify a crater in this particular region. And so we went about quantifying this. So here we can see the change over time. The time is sort of meaningless because we really don't know what the weathering rate on Titan is. So for now, the time will be unitless. But you can see again that over time, our nice hole in the ground turns into something that is pretty much flat. Okay, and it would be difficult to identify from orbit using an orbiter like Cassini. So although you could probably pretty easily see something like the image at top left, identifying something like what we're seeing at the bottom here as a crater would be incredibly difficult to do, especially given the low resolution of the images we have from Cassini. So we plotted the results over time. What you're seeing here on these plots on the left, we have the relative depth on the y-axis. So 0 is a fresh crater, and 1 is a completely flat crater. Okay, the lines that you're seeing here are the results of those models. And then I've plotted over that the depths of craters on Titan. So SynLab is over here on the left, and Soy is over here on the right. And what we notice is if we compare the timing of when we get a crater the depth of SynLab, it actually produces a very similar morphology to what we're seeing on Titan. We have a little bit of a remnant of that central peak left over, which you can see is this one bright pixel here. Meanwhile, if we were to erode it to the depth of Soy, we find that the central pit is completely eroded. And the morphology is, obviously the rim is incised, so there's holes in the rim. This is all very consistent with the results of the model. So fluvial erosion appears to be, at least if not the main process degrading craters on Titan, an important secondary process, given the morphologies we observe from our landscape evolution model. Here's another image of that central peak. So here's our degraded isis with the same depth as SynLab, which has this little remnant of the central pit. And here is an image from the Cassini visual and infrared mapping spectrometer. And again, you can see that little remnant of the central peak. It's a little bit more obvious than the one bright pixel we see in the radar image. So at least morphologically, it seems like there is a relationship between fluvial erosion and the degradation of craters on Titan. In order for this to completely erase craters near Titan's poles, we would need to have a weathering rate that's several times higher near the poles, which isn't out of the question. You know, a small change in weathering rate might be expected if you have slightly more precipitation near the poles. So this seems like at least one reasonable explanation to account for the lack of craters on Titan. But in fact, my favorite explanation might be the fifth one, which I haven't yet talked about. And that's this idea of marine impacts on Titan. So let me set up this problem for you. So here's another map of Titan. This is the elevation map of Titan. So red areas are topographic highs, and blue areas and purple areas are topographic lows. And what you notice is that the equator is typically has higher elevation than the poles, and that most of the craters on Titan are found at those higher elevations. So what could explain this? Well, here's one example to kind of lead into this question. This is an impact crater, and I imagine all of you know exactly where the impact crater is based on this image. Obviously not. It's almost impossible to see the impact crater in this image. This is the Chesapeake Bay impact crater, which was not discovered through orbital imagery, but rather through techniques that you could only find on Earth, drilling, seismic surveys using airplanes, a lot of really in situ techniques that we can't use for other planets. And what they discovered, and perhaps one of the best journal paper names I've ever heard, is this 85-kilometer impact crater just here in Northern Virginia. This was detailed by Pogue et al. In his paper Meteorite Mayhem in Old Virginia. So I'm quite impressed that he was able to get that name published in geology. But again, if we flip back and forth, there's almost no morphologic evidence that this crater exists from orbital imagery. And this is because of the way that impact craters are formed in liquids. So when an impact strikes a liquid layer rather than a solid layer, the material slumps right back into the crater immediately after formation. So this is some modeling that was done for Chesapeake Bay by Gareth Collins. And you'll see that at first you form that nice bowl-shaped crater that you're used to, but then over time that sediment slumps back into the crater, filling it in. So a couple minutes after its formation, it's already pretty much flat. So these craters form flat. They never have that nice bowl-shaped expression that we expect for craters formed on land surfaces. In case you don't believe the models, here are some experiments where they did something very similar. They impacted dry sand at the top. Again, there's your nice bowl-shaped crater. But then at the bottom, they impacted into saturated sand and sand underwater. And in both of those cases, it's incredibly difficult to identify the impact crater because of this slumping by the sediment in the wet materials. And the reason a lot of people haven't thought about this in planetary science is because there aren't a lot of places in the solar system with liquids on their surface. And in fact, as of the present day, only Titan and the Earth have standing bodies of liquids on their surface. So let's go back to this map. Okay, so now that we know about marine impacts and how they form, this map makes perhaps a little bit more sense. If we were to form if we were to form an ocean on Titan, it would presumably go in the regions of lowest elevation. So perhaps the reason we don't see impact craters near the poles is because there used to be an ocean there, or the ground surface is saturated in liquid hydrocarbons. So for a wet Titan, you'd expect to form craters in the dry highlands, and they would remain unobserved in the lowlands. They simply wouldn't form in a way that you could observe from orbit. And there's been some work to think about how long these oceans might last. And given that the current rate of destruction of methane, you might think that Titan looked a little bit like this several hundred million years ago, with an ocean that covered the poles, dipping down a little bit into the equatorial regions, but preventing craters from forming in these wet polar regions. So what's the punchline? Well, when we look at Titan's craters, we find that they're predominantly found in the highlands near the equator. And the two best hypotheses for explaining this distribution seems to be either there is increased fluvial erosion near the poles, or that Titan used to be covered in a polar ocean and that impacts formed in a marine environment, leaving no trace of their impact behind. So let's wrap this up. What does this tell us about Titan and its geologic history? So I'm going to try to tell you a little story here in the last few minutes of this talk, which I think might tell us about how Titan formed. So let's go back in time, maybe, let's not go back in time just yet. All right, so what has happened to Titan over time? Well, it's possible that there have been outbursts of methane, so that the methane has not been constant in Titan's atmosphere over its history, but that things happen to Titan that cause methane to be injected into the atmosphere and then to decay slowly over time. And here's one model proposed by Gabriel Tobey in 2006, where overturn in Titan's core actually leads to outgassing of methane. That methane then gets depleted through the processes I mentioned earlier until another outburst comes along and injects more methane into the atmosphere. And their prediction was the last outburst happened perhaps 500 million years ago. Okay, so what does this mean about how Titan has changed over time? Well, it started a billion years ago. If Tobey's model is correct, Titan did not have any methane in its atmosphere. It had a thick nitrogen atmosphere but no methane. So the predominant processes at this time would be perhaps some impact cratering, maybe some fluvial processes with nitrogen, which is completely alien to think about, but no methane, no liquid hydrocarbons, no haze. You could say that Titan looks like Ganymede with weather, which is a takeoff of my colleague's paper called Titan Callisto with weather. I think Titan has been more active than Callisto. I digress. Okay, so then 500 million years ago, maybe there was this large burst of methane. Okay, so it still has had time to erode the surface, but now we have that hazy material in Titan's atmosphere caused by the destruction of methane. Okay, so now we're going to start to get methane condensing out of the atmosphere, forming streams and lakes and possibly oceans. Okay, so then a few 100 million years later, now Titan is, again, this wet ocean world, perhaps, covered in liquid hydrocarbons, extending down perhaps close to the equator. But then, the course of time, the methane keeps getting depleted, lost to space, slowly, turning Titan into the dry desert world that we see today, with only remnants of the ocean found near the poles, but most of Titan very dry and covered in sand dunes, where the predominant process today is that alien infilling I was telling you about. So this tells you perhaps one story about how Titan formed and how the craters on Titan were able to inform us about its history. So what's next? Well, I'd love to test some of these ideas. And one way to do that is with another mission. There have been several proposed missions to Titan, several of which were not selected. This was the Titan Mare Explorer that you see here. That was a proposal to NASA's Discovery program in 2012 that sadly did not get selected. It would have sent a boat to one of Titan's polar oceans. But there is a new opportunity right now through NASA's New Frontiers program, and so it's possible that we might see a mission to Titan in the near future that could investigate some of the issues that have been raised in the era post-Cassini. So with that, I will wrap up my talk and thank my collaborators as well as you for your attention. Thanks very much.
Yay. Can we dive in and ask you questions, Catherine?
Mm-hmm.
Okay. First of all, that was a fantastic talk. I'm like really stoked on Titan right now. So I have a bunch of questions. I'll ask you just two of them, and then you can answer whichever one is more fun. So, what the heck is the sand on Titan? Is it just like little bits of ice? So that's question number one. And the other one is, what causes the pits in the craters on icy moons? Like, why do they have those pits and we don't see those on rocky planets?
The first question you asked could be called the billion-dollar question, right? Because we really need a spacecraft to return to Titan to answer it properly. All we know is that they are made of organic material, not ice, and that they're the right size for sand. So there's this sweet spot that you need a sand particle to be, so it's not so light that it will just sort of hover in the atmosphere like dust, and it's not so heavy that that it won't get picked up by the wind. So there's this sweet spot. It's about 200 microns. So we have organic particles that are about 200 microns large, and that's all we know about the sand on Titan. We have no idea how it was formed, and to investigate that, we really need another mission. Your second question about central pits on icy satellites is, again, another open question. One hypothesis I've seen for the formation of central pits is actually drainage of melt. So unlike rock, where the liquid is less dense than the solid, the opposite is true for ice, right? Ice is less dense than water. And so you can imagine a scenario where you form water during the impact and then it drains out the bottom through fractures, forming the central pit. So that's one idea.
Are there any questions here in the room at work? I see one.
Hi. So I know that you're super interested in Titan. What is it about Titan that drew your interest as opposed to some of the other like large satellites that also have strong possibilities of hosting organic materials like Enceladus or Io, or whichever moon is covered in ice, it has the liquid water underneath.
Right. So I would argue, though, that Titan is probably the best place to look for life in the solar system, because for life to form, you need not just water, you also need organic molecules. And most of these other icy satellites, either we have no idea how many organic molecules are there, or it's unlikely they're there at all. And so water is not alone to produce life. You need organic molecules, and Titan is covered in organic molecules. There is a huge abundance of organics there. And as I showed in my PhD, if you mix those with water, it's very, very easy to form biological molecules. So these lava flows and impact melts on Titan, I think, are some of the best places to go looking for life in the solar system. And that's honestly what first drew my attention to Titan, was that sort of astrobiological aspect to it. But then, over time, as we got more and more data back from Cassini, I also got very interested in its geology and how similar it is to Earth, and how we can use Titan as this sort of bizarro analog for understanding processes that happen on Earth under very different conditions, with very different materials, yet somehow form similar features. So it's a great example of comparative planetology.
One in the back here, York.
Hey, what's the significance of the geographic distribution of sand dunes on Titan? Is that something that could be caused by wind patterns? And do we know anything about wind patterns on Titan?
Yeah, a little bit. We don't know. It's all concentrated near the equator. I don't think it's wind alone. I think moisture content also probably plays a role. The poles are very wet. The equator is likely very dry. So that might play a role here in why we see more sand dunes near the equator than the poles. The wind regime is something that's been a topic of research and debate for the past decade, primarily because the first models of Titan's wind showed that wind should go one way, and the sand dunes indicated it was going the other way. And so we had the people observing dunes and the people modeling wind totally disagreeing with one another. And it wasn't until very recently that they showed that although the wind typically goes one direction, it will switch seasonally to actually line up with the direction we see the dunes going. But I don't think that's why we see the dunes necessarily at the equator. I think it has more to do with how wet the soil is.
I have a question here from Miguel. Can you hear us?
Yep, I can hear you.
Great. The methane outburst, two questions. One, what would control the timing of that? And number two, why methane dominated and why not other gases?
Well, methane probably has to do with basically how the sun was condensed billions of years ago. In the outer solar system, methane is preferred over carbon dioxide as the carbon-bearing species. You expect to see more methane in the outer solar system. In terms of the outbursts and what controls that, in Toby's model, he was proposing that there was differentiation occurring in Titan's interior that caused outbursts. It's unclear how applicable that model is anymore now that we know more about Titan's interior, and it's probably not as differentiated as we originally thought. But that was what he was proposing anyways, that there was differentiation going on.
Yeah, what causes one is what causes the topography from the pole to the equator, like why is it the highlands and the lowlands? And then the second one is impacts. Can you actually get some weird minerals forming?
I didn't hear the second question. Sorry.
When these impacts occur, can you get some strange mineralogy occurring, like graphites or diamonds or something?
Well, again, remember these are impacts. So you're not getting any silicates or anything like that forming. You may get some weird chemistry between the organics and the water, though. Again, Titan is so different from any other planet. You have to kind of wrap your brain around this new paradigm. And so you could have sort of the equivalent of hydrothermal systems on Titan, but the working liquid would be methane in sort of this hot ice background. And who knows what, honestly, I have no idea what would form in those scenarios. We have no analogs like that on Earth or any of the other terrestrial planets. Let's see, for your first question, the topography on Titan, well, primarily it's shaped by Titan's spin. So when a planet spins, the poles flatten to form this sort of oblate spheroid. This is true for every rotating object in the solar system, including the Earth. But even when you subtract that oblate spheroid, the poles are still suppressed. And we don't know why they're lower, actually, than the rest of Titan. There's been a couple ideas proposed, but I think that remains an open question on Titan.
Any other questions here in the room? Do you want to call it, Nick?
Yeah, I think we're good. Thanks again, Catherine. That was fantastic. And we'll see everyone again in the coming weeks. We'll send out, I think Nicole's going to send out announcements